Hello, everybody. This is Mr. Tam back with another episode of Science. Now, today we're going to explore something very different from our usual content for just a regular science and technology course. This is for all you students who are doing the secondary for science, environmental science and technology course, or we can refer to it also as the enriched portion of the course if you're planning to do chemistry and physics next year. So, what I'd like to introduce to you guys today is a very fancy word that, upon me saying it, seems to invoke some kind of panic or nightmarish scenario, kind of like nightmare fuel. But apparently, no matter how I put it, you guys somehow freak out a little bit. But not to worry, we're going to walk you through that today. And this topic, of course, known by many as stoichiometry, or we can call it just stoic for short. And stoichiometry, I mean, the theory behind it is that you're just using it as a prediction tool to compare the amount of reactants versus the amount of products in a reaction. So it's basically the calculation of amounts of reactants versus products. So that's basically what stoichiometry's objective aims to do. That if you're given a certain amount, you can use that amount to predict how much of something else you'll need. So I always go back to pancakes because those are one of my favorite foods. And the idea behind the pancake analogy is that if, let's say, I have a recipe in front of me that is written out, and let's say I'm limited by a certain amount of one of the ingredients, say flour. Well, I can use that limited amount to be able to predict how much of everything else I need to be able to use up that amount of flour. So I can predict exactly using, let's say, 100 grams of flour, how much milk I need, how many eggs I need, et cetera, without actually altering the amount of flour I need. Okay, so it's like given a recipe, I can follow the recipe based on what I actually have. So I'm going to give you just one simple example today. That's all we'll do for introductions. And hopefully we'll go into some more complex problems as we go along. So just as a little refresher, you guys have done this in the past. And this is something called balancing equations. Now, I don't know about you guys, but I've practiced these so much that, you feel comfortable with it. And that's what you guys need to do. Balancing equations is absolutely crucial to stoichiometry. So when you see an equation like this, we call this a skeleton equation, basically because you have no coefficients or numbers written next to each of these molecules, neither on the reactant side or the product side. So we have to fix that because whatever quantity is on the left has to be equal to the quantities that's on the right. That is what we call the law of conservation of mass. So just a quick technique to remind you guys that I like to write the elements underneath the arrow, and I like to write out the initial amounts on each side. So I write it out like this, nice and easy. And then on the other side, carbon has 1, hydrogen has 2, but the oxygen, be careful, has 3. And what I usually like to do just off to the side here, because I don't know how I'm going to change the 3, but I do know that the 3 is made up of the 2 and the 1 together. So I can actually track it when I go to change things because it's located in 2 different places. So I always start with elements that are not hydrogen or oxygen. It just seems to be a good rule of thumb, where if I take the 3 next to the carbon on the left, I know that the only thing I'm ever allowed to do is to put a coefficient in front of a molecule, which means that if I wanted to fix the carbon to match, I'm going to put a 3 in front here. And this allows me to scratch out the 1, put a 3. But at the same time, because I put a 3 in front of here, 3 times 2 gives me 6. So that 6 plus 1 now turns into 7. So I know the carbon's checked off because both sides have the same amount. Next thing I'm going to do, logically speaking, is fix the 8 because I can see that with the hydrogen, there's 8 on the left and 2 on the right, both of which are even numbers way easier to fix. So I'm going to do exactly that by putting a 4 in front of my hydrogen. And that leads me, of course, to 4 times 2, which gives me 8. But now, because there's a 4 in front of the H2O, the 4 times 1 gives me 4 here. So this number changes yet again to 6 plus 4, which gives me a grand total of 10. And you say to yourself, man, Mr. Tam, 2 and 10, they're both now even numbers. Well, that's fantastic because even numbers are easy to fix. What number do I have to multiply the 2 by right here in this oxygen to give me 10? Well, that answer is 5. And once I multiply that oxygen gas by 5, that ends up giving me a grand total of 10, which essentially just balances my equation. Fantastic. This is very, very good news. So I'm now just going to get rid of the writing that I have here and use my balanced equation. So this is where the balanced equation comes into play. I'm going to give you a simple stoichiometry reaction here, or a stoichiometry amount. If you have 12 moles of CO2, or atoms, or yeah, we can use, you know, we have 12 molecules of CO2, we have 12 moles of CO2, it doesn't really matter. We're going to try to predict the amount of, and I'm going to do this in I'm going to break this up into 3 parts, guys, because basically I've been given 12 moles as my amount here. My job is to try to predict everything else. So I'm going to ask you first to predict the amount of propane. Now, propane has a molecular formula of C3H8. And the C3H8 has a coefficient of 1 next to it, huh? Let's put that little 1 to remind ourselves that indeed there is a 1 before it. I put it as a dotted one because it's not usually something we write, but visually to help myself out, it makes it a lot easier. So to help myself find out the amount of propane I can make with 12 moles, or the amount of propane I have to use to make 12 moles of CO2, I set up first my ratio versus actual. Okay, so ratio means I take the coefficients that I see here and here, the 2 things that I care about. So in this case, I do 3 moles of CO2 using the coefficient, and I know that for every 3 moles of CO2 that are produced, I need to use up 1 mole of C3H8 or propane. It's like saying, oh, I have to make 3 pancakes. Oh, I need 1 cup of flour. But that's the ratio. That's kind of like the recipe. But what if I don't actually have that? What if I have way more of the pancakes I want to make? Well, I got to increase the amount of flour as well. So it's the same thing here. If I wanted to make 12 moles of CO2, which is the actual amount I have, well, I don't really know the number of moles of propane. Well, if you guys, I mean, if this kind of tickles a funny bone or kind of raises a little red flag to say, hey, wait a minute, sir, I've seen this before. This is cross multiplication. Well, 3 times n ends up giving you 3n. We're just going to kind of leave those units out for a second there. And 12 times 1 gives me 12. And if I isolate for n, of course, because you guys are so used to doing this, I'm left with 4. Now, of course, you're saying to yourself, well, for what? Well, the reason I always ask you guys to write those units next to your setup is because there's no guesswork involved if you do that. So this actually ends up being 4 moles of C3H8. Fantastic. So knowing that I have 4 moles of C3H8, I'm ready to move on to part number 2, where now I'm interested in finding the amount of, let's say, oxygen that I need. So oxygen, the number of moles of oxygen I need. So you can see that the moles of oxygen are slightly different. For the moles of oxygen, well, there's a couple of ways to do this. There's no, one right or wrong way to do it, but there's a reason I asked you guys to do propane first. If you notice, We always go by ratio. So this is a 3-to-1 ratio, which means that for the propane, it's 1/3 of what we had before. So if we had 12 before, well, the propane used up 1/3 of that. Well, if you compare the ratios of oxygen, for example, in this case, 5 moles of oxygen to the 1 mole of C3H8 or propane, you say to yourself, hey, gosh darn, sir, that looks like there's 5 times as much oxygen that I need to react with the propane. And you'd be absolutely right. Now, given that there's 12 moles of CO2, I know that there are 4 moles of C3H8. This is what I found from this number right here. That's why I'm able to transfer that over here. So to figure out how many moles of oxygen, I have an unknown number of moles here of oxygen that I lined up. And when I go to cross multiply it, n times 1 gives me n, and 5 times 4 gives me 20 moles of oxygen. And last but not least, so this is one way of doing it. Last but not least, I'm going to ask you guys to find the amount of water that's also produced. So some of you may say, sure, that's a bit convoluted. I have to use the information from before. All right, if you're not happy with the information from before, we're going to use 2 different ratios. So this is the ratio versus actual method. So the ratio you actually have, let's say we're using the 12 moles of CO2, is that, well, you do have 3 moles of CO2, and it also at the same time produces 4 moles of H2O. And this is based on us looking at our balanced equation. But the actual amount of CO2 I have is 12 moles because that was my original question. And I have an unknown number of moles of H2O. So when I go to cross multiply this, of course, I'm going to do it up here because I am running out of room a little bit. 3 times n is equal to 3n, and 12 times 4 gives me 48. And when I go to solve for n, of course, dividing both sides by 3, I end up with n being, drum roll please, 16 moles. Of what? Well, you already fixed the problem by writing the units next to it, 16 moles of H2O. So what's nice about stoichiometry, and this is just, of course, the very basic form using mole ratios for stoichiometry, is that we can use one amount, and this was the 12 moles of CO2, to be able to predict every other ingredient that's in there, be it reactant, which are the actual ingredients in my pancake, or my products, which is, of course, the pancake itself. So this is Mr. Tam signing off, hoping that this helped you guys out and that you guys are keeping well in these troubled times. Take care, and I will see you in the next episode. Take care. Bye-bye.